Hello world, it's Craig. I used it in my last video, but I didn't really explain the decimal adjust accumulator instruction. And that instruction may not be that familiar to everyone. Now, DAA first showed up in the 8080 and the 6800 microprocessors, and it's used during decimal addition to convert the result back into a decimal value. The processor, of course, is just doing all of its addition in binary. Give it two numbers like 0010, and if we're going to add 0111, and it'll give us the result 1001. We would generally agree that that answer is 9. But now if we add something to that, like another 9, 1001, the computer will give us 10010. Now we may begin to disagree what the number actually is. Is it 12 in hexadecimal? Or is it 22 in octal? But those are just different interpretations of the same binary value, so there's actually no disagreement in those. But if I tell you that the addition we just did was a decimal addition, then this is going to be a completely different number. And it can't just be interpreted as decimal, it must actually be converted to decimal. 9 plus 9 in decimal is 18, meaning the two nibbles should be 1 and 8, not 1 and 2. Now that is the function of the DAA instruction. It will take the result of an addition and convert it or adjust it so that it is the correct decimal value of that addition. In this case, it would take the 12 and it would adjust it to be 18. Now, processors like the 8080 do not have a set of instructions for binary addition and then another set of instructions just for decimal addition. So you need to think of the DAA instruction as a suffix or an add-on to the add instruction. So DAA tells the processor, it says, hey, that addition we just did, it was a decimal addition. So the processor can then do a conversion of the result into packed binary coded decimal. By packed, we mean the two decimal digits are sharing the same byte. Each digit is one nibble, and the digit on the left is an order of magnitude larger than the digit on the right. So normal stuff. If this is the ones, then this one over here is the tens. If this is the hundreds, this is the thousands. Now, binary coded decimal, or BCD, means the digits are directly representing their decimal value. They don't need to be converted. 1 is 1, 5 is 5, 9 is 9, and anything larger than 9 just doesn't exist. So there's no A, B, C, D, E, F stuff here. The DAA instruction has to immediately follow the add instruction before the processor forgets how it did the addition. Those flags can't be reset. Specifically, it needs to still have the carry flag and the half carry flag, which Intel calls the auxiliary carry. We routinely use the carry flag, but the auxiliary carry flag is only used for the DAA instruction, so many casual programmers don't even know that it exists. Now, the auxiliary carry is not mystical. It simply indicates that during the last add instruction, the lower nibbles of the accumulator rolled over 1111, and a bit was carried to the high nibble, exactly the same way that the normal carry indicates that the byte rolled over and set the carry bit. In practical terms, what does the DAA instruction do? First, it considers the low nibble, and if that value is not a valid decimal digit, meaning it's greater than 9, or if the auxiliary carry was set during the addition, then the DAA instruction will add 6 to that nibble. Then the DAA does the same thing to the high nibble. If that nibble is above 9, or if the carry is set, then it adds 6 to the high nibble and sets the carry. When the DAA is complete, the two carry flags are set according to whatever happened during the instruction. So if the low nibble rolled over, then the auxiliary carry flag will be set. If the high nibble rolled over, then the carry is set. Typically, we don't care about the half carry anymore, but we probably need to account for the full carry in our next instruction. I keep saying the auxiliary carry is affected by the addition instruction, which is technically true, but it's actually affected not only by the addition, but also subtractions. The increments and decrements, all of the logicals, and the compares, and of course, it's affected by the DAA instruction itself. This is because nearly all of these involve additions. When the processor does subtraction, it's actually doing a 2's complement addition. So either the 1's complement conversion or the increment up to 2's complement can trigger a rollover on that half carry. When the processor does a compare, it's actually a subtraction, which is actually an addition. Now the logicals are a special case. They mostly set the 2 carry bits to 0, and it's a tiny thing, but in the 8080 and the 8085, they handle the half carry differently with an AND instruction, but for the life of me, I can't see how that's ever going to come up. A bit more on the process of adding 6 when the digit is above 9, or if the full or half carry is set. The above 9 case is pretty obvious because A through F aren't decimal digits. But why add 6 if the carry is already set? If the addition were, say, 9 and 9, like the example I gave earlier, at first glance, the value in the accumulator, 1, 2, looks to be a valid decimal value. But during the addition, the result went through all of the decimal numbers and then through the rest of the hexadecimal values A through F and then back into the decimal digits again. So even if the result are decimal digits, there's 6 decimal numbers that are missing when the processor was in the A through F space. The DAA needs to unwind that by looking at the auxiliary carry flag. And at this point, when the nibble was 1010, the result was actually 10 in decimal. So 1011, it was 11, and so forth. 1111 was 15, 0000 was 16 until it finishes up at 0010, which is actually 18. Now, this isn't the processor's first rodeo, so it knows the easiest way to adjust for this is to just increment the high nibble because it passed 10, so there was a carry, and then fudge the low nibble by adding 6 to make up for those missing decimal digits that were skipped when the number was in the hexadecimal territory. The same for the high nibble and the full carry flag. So let's finish up with an example. If the addition were this, 0110, 0110, which is 66 in hex, plus 0101, 0111, 57 in hex. That addition is going to give us 1011, 1101, which is BD in hexadecimal, or 274 in octal if we think that way. But in decimal, 66 plus 57 is 123. After the addition, the auxiliary carry flag was set, but the full carry, the regular carry, is not set. The DAA does the bottom nibble. It will add 6 to get EF0, 1, 2, 3 in the bottom nibble, and it will set the auxiliary carry because there was a rollover. Now that 6 it added was to the entire accumulator. And so the carry already went over into the high nibble. Now it's going to add 6 to the high nibble, or 60 to the entire accumulator. So DEF012, and the main carry will be set so it can be taken over into the next higher digit by the program. As long as we remember to include the carry in the hundreds position, we can now directly read and interpret the accumulator as 123 in decimal. If we're doing another add instruction, then we would probably want to do the add with carry followed by another DAA and so forth. Alrighty, well that is it for this video. I just want to make sure we are on the same page with the DAA instruction because my next video is going to be doing the binary to decimal conversion again, only this time we're going to use the double dabble method. Now double dabble doesn't use the DAA, but it's easier to understand double dabble if you already understand the DAA instruction. As always, this channel is not monetized and entirely funded by likes, shares, subscribers, and comments. Talk with you later. Thanks for watching. Bye-bye.